Now let's move ahead with the third dimensionality reduction method, which is linear discriminant analysis. Linear discriminant analysis is a dimensionality reduction and classification technique used to find a linear combination of features that maximizes the separation between the classes in a dataset. So Ronald A. Fisher formulated the linear discriminant in 1936, the use of multiple measurements in taxonomic problems. And it also has some practical uses as a classifier. The original linear discriminant was described for a two-class problem, and it was then later generalized as multi-class linear discriminant analysis or multiple discriminant analysis by C.R. Rao in 1948. So let's define and explain LDA. So linear discriminant analysis, or in short LDA, is a dimensionality reduction and classification technique used to find a linear combination of features that maximizes the separation between classes in a data set. It is a supervised learning algorithm commonly used for classification tasks, especially in the field of pattern recognition and machine learning. So next, history. Let's look into the history of LDA. LDA was first introduced by Ronald A. Fisher in 1966 as a statistical method for distinguishing between two or more classes. Then the original linear discriminant was described for a two-class problem, and then it was later generalized as a multi-class linear discriminant analysis or multiple discriminant analysis by C.R. Rao in 1948. It has since become a widely used and well-established technique in the field of statistics and machine learning. Now let's look into some of the assumptions that we have to take up before you work on LDA. So LDA makes several assumptions about the data. One is linear separability. LDA assumes that the data can be separated by a linear boundary. And second one is normality. LDA assumes that the features of each class are normally distributed. And the third one is equal covariance. LDA assumes that the covariance matrices for matrices of all classes are equal. Now applicability. So LDA is applicable to labeled data where the class labels of each data point are known. So it's commonly used for classification tasks such as face recognition, text categorization, and medical diagnosis. So LDA can also be used for dimensionality reduction to visualize high dimensional data to improve the performance of machine learning models by reducing the number of features. So now let's look into the mathematical equations or the formulas that we use in linear discriminant analysis. The goal of LDA is to find linear combination of features that maximizes the between class scatter while minimizing the within class scatter. Given a data set with d-dimensional features and n data points, the LDA transformation can be represented by the LDA transformation can be calculated by the following formula. So LDA solves the generalized eigenvalue problem for the matrix following matrix to obtain the linear discriminants, which is LDA solves the generalized eigenvalue problem for the following matrix to obtain the linear discriminants using S sub W of inverse multiplied by S sub B. So this is gonna solve our problem. So where S sub B is the between class scatter matrix and S sub W is within class scatter matrix. What we are gonna do is let's deep dive into it in detail to have a clarity what is S sub W, S sub B. So first we have to compute the mean vectors. So mean vectors, first calculate the mean vectors for all classes inside the dataset. Whatever classes you have inside the dataset, for all classes you have to calculate the mean vector. So it can be calculated using mean sub I, so which is m sub I is equal to 1 by n sub I and summation of I to I is equals to 1 to n and x sub I for all features it has to be done. Then once computing the mean vectors are done, now it's time to compute the scatter matrices. After calculating the mean vectors, now it's time to do within class and between class scatter matrices can be calculated. So first we will calculate the within class scatter matrix within SW is within, S sub W is within class matrix. So S sub W is equal to sigma of I is equals to 1 to C and S sub I. Here S sub I is the scatter matrix for specific class. So what is S sub I? Then how you calculate? So this can be calculated with the summation of multiplication of x minus m sub I. This is mean of the respective class and x multiplied by x minus m sub I transpose of the same matrix. So m sub I is the mean vector for that class that we have discussed earlier. So and this is how we calculate. Then alternatively, the class covariance matrices can be used by adding the scaling factor 1 divided by capital N minus 1 to the within class scatter matrix. So finally, bringing up all together, you will get your S sub W. So S sub W is nothing but sigma I is equals to 1 to C n sub I minus 1 multiplied by respective component that you can see on the screen. Then now let's calculate the between class scatter matrix. It's slightly easier than compared to that. So between class scatter matrix is equal to sigma I is equals to 1 to C and n sub I and multiplication of a mean vector sub I minus mean multiplied by mean vector sub I minus mean old transpose. So where m is the overall mean and m sub I is the mean of the respective class and n sub I is the sample size of that class. So now it's all done. It's all set now. It's time to calculate the linear discriminants. Next, LDA solves the generalized eigenvalue problem for the matrix S sub W inverse multiplied by S sub B to obtain the linear discriminants, and this is what the mathematics goes behind the LDA linear discriminant analysis. Let's move ahead. So now it's time to look into the algorithm working process. So the LDA algorithm can be summarized in 5 steps. The first one is to calculate the mean vectors for each class. We have seen how to do that. Then calculate the between class scatter matrix S sub B and within class scatter matrix S sub W. Then find the eigenvalues and eigenvectors of the matrix of S sub W inverse. Obviously that's what we did here, that you can see S sub W inverse multiplied by S sub WB which is S sub B, which is we can find the eigenvalues and eigenvectors of this product. Then all done. It's time to select the top k eigenvectors corresponding to the k largest eigenvalues to form the transformation matrix W. Then project the original data onto the lower dimensional space using the transformation matrix W. So now let's look into some of the real life examples where we can use this and where we can take the leverage of this LDA linear discriminant analysis. So the first one, Face recognition. LDA is used to extract discriminative features from face images to identify individuals. Then text categorization. LDA can be applied to transform text data into a lower dimensional space for document categorization tasks. Then medical diagnosis. LDA can help classify patients into different disease categories based on the medical features. So overall, linear discriminant analysis is a powerful tool for dimensionality reduction and classification tasks, especially when the data has distinct class structures. However, it is essential to ensure that the underlying assumptions of LDA are met before applying it to a particular problem.